Hey folks, I'm about to get started here. I'm still feeling really sick. I have a brand new cough, and so we'll see how this goes. It's whoa, no, let's turn that off. I'm having a little bit of a hard time talking because of my scratchy voice. Let me turn off this. Why is it coming out of there? Hang on. Hang on. What's going on here? Let's try that. First, hello, Grudge Monkey. Let me make sure I can hear. So my the audio just went crazy here. It went out of the wrong device. Let me make sure. Let me make sure it sounds okay on the screen. First of all, how many of these are there? Okay. All right. Seems okay. All right. So we're gonna look at Bochs first, which is let's do the intro. Hello and welcome to Answer Everywhere. Today we are taking a look at Bochs, which is an IA32 emulator. IA32 should be just the same as x86, the 32-bit Intel architecture. Bochs is like way old, 23 years old according to GitHub, if we believe GitHub, and is hosted on SourceForge, which suggests it's pretty old. And the website also looks pretty old. I think I have Dark Reader on. So let's look at Bochs. They've got a wiki. Look at that. A portable x86 PC emulation software package that emulates enough of the CPU-related AT hardware and BIOS to run Windows, Linux, BSD, Minix, and other OSs, all on your workstation. And so here's Bochs with 2 CPUs. So I guess this is like a virtual machine. I'm not sure what makes it an emulator as opposed to, for example, a VM, but we'll see, I guess. And it seems to be running Windows. So maybe let's look at maybe the frequently asked questions. How do you pronounce it? Like Bochs. Why can't I use it? Blah, blah, blah. Okay, so let's take a look. Right. Bochs is an emulator, not virtualization software. So there we go. That's the answer to the question I had. It's portable across blah, 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 blah. This means it must be able to emulate every CPU instruction. Okay. So I guess the idea is that since they wanted to be able to target CPUs like ARM and MIPS that aren't x86, they have to emulate. Whereas I guess virtualization can only like mimic the same architecture. Is that right? I think that might be right. Let's see, like cross architecture virtualization. I think that's not necessarily a thing. Cross-platform virtualization. To run unmodified on computers with two different CPUs and or operating systems through dynamic binary translation and operating system call mapping. Okay, so that's a different thing. So I think that you need like extra work to make that sort of thing work. You need some translation later. Okay, so Bochs is an emulator. In the default folder, we have only a handful of folders. So Bochs is the obvious one. Bochs testing is maybe mildly interesting. We really just have plugin test. Bryce created this CVS area on October 11th, 2002, as a place to work on Bochs test code without cluttering up the source tree. Seems like it's not really used. All right, so let's take a look. Let's focus on this Bochs/Bochs folder. We have BIOS, build. Build is, I'm going to guess, for building the Bochs software project. CPU, GUI. I guess Bochs, as an emulator, has its own GUI. And that may not be the most important thing. Host/Linux/PCI dev. Something about PCI devices. And instrument is probably not so fundamental. IO dev, memory, miss, and patches. And then what do we have in terms of... We have, let's see, I'm seeing a few shell scripts. Also a few CC files. But not a ton. We have this RC file. Some QEMU stuff. Plugin, main. Should we look at main? I guess we might look at main. And I'm going to guess that most of the cool stuff that we want to see is in CPU, maybe memory, and possibly BIOS. So I'm going to open up those. This RC file, I'm not sure what it is. I'll ignore it. Main.cc. So how big is this? 1,421 lines of code. So not huge. Let's scroll to the bottom. This looks like a, no, it's not. So this Bochs signal handler. And we've got this comment: in a multi-threaded environment, a signal such as SIGINT can be sent to all threads. This function is only intended to handle signals in the simulator thread. It will simply return if called from any other thread. So this is just some signal handler, IPS and handler, dialog stuff, some stuff for getting the timestamp, which is mainly calling sprintf, and so on. Okay, so far main doesn't seem so fascinating. Let's look at CPU and maybe pull it out into its own window. AVX, I don't know what that stands for. CPU DB, I'm going to guess debugging. Decoder, FPU, soft float. And what? The AES, I'm going to guess, is the support for the encryption standard. CPU.h and CPU.cc, let's look at those. CPU ID. CRC32 should be the checksum, I guess it's called. We have data transfer 16 and data transfer 32, data transfer 8. Should we poke at a couple of these? And also control transfer. Maybe let's look at data transfer and control transfer for a couple of these. Event. I'm not sure how important event is. Let's look at, I guess, FPU. I don't know if that's floating point unit. IC cache. I guess. Init. Sure, why not? IO. Jump far.cc. Logical. I guess let's look at load and logical. Mult might be multiplication. I don't really know what MSR is. MMX, I forget what that is. RDRAND should be the random number generator. Scalar arithmetic. Segment control, SHA, should be the hash, I would guess. Shift 512, Shift 8. Let's look at Shift. Here's some SIMD stuff, I guess. Stack might be fundamental. I don't know what stack 16 versus stack 32 versus stack 64 is. Some stuff with tasking. Let's ignore tasking. To do, we can ignore. And And I guess that's enough for now. I'm not sure how in depth we'll get at any of those. And then I guess let's look at memory. Well, we mainly have memory CC and memory box. Let's look at, we'll look at those first, I think, but then let's open some stuff in BIOS. So BIOS seems to be, I don't know. I don't know what Elpin is. CBIOS, I think CBIOS is like a lightweight BIOS for like emulators. An open source implementation of the 16-bit x86 BIOS. It can run in an emulator. It can run natively on x86 hardware. Okay, so this is some sort of CBIOS, I guess. Compatibility. The core boot CBIOS page has information, blah, blah, blah. C VGA BIOS is a subproject. Okay, so I'm guessing they're just mainly using this other BIOS. So let's take a quick look in memorybox.h and what is this, memory.cc, and then we'll move on to the CPU stuff, which I imagine is what is the most interesting. And then they'll probably take us into about an hour, at which point we will stop looking at this, either move on to another repo or I might have to quit if I'm not feeling well enough. Okay, so memory box is a bunch of enums and, well, we get a class here. What is this? Box API bxmemc, extending public memory stub C. bxmemc, box mem, I don't know if C is for the C language. We've got a memory handler struct. So we've got some list of handlers. Whether PCI is enabled. I'm not sure what PCI is. Oh, it's like yeah. PCI configuration space. What does it stand for? Peripheral component interconnect. A local computer bus for attaching hardware devices on the computer and is part of the PCI local bus standard. So I guess this is support for the PCI bus here, or not support for, but it's a flag indicating whether it's enabled, whether BIOS write is enabled. Some stuff about SRAM. ROM present is a bool that's an array of 65 bools. 64, you could represent 64 bools with an int. I don't know why they need 65. And I'm also not really sure what ROM present is. I don't know if this is supposed to be modeling the ROM or something else. Like modeling the, I don't know if a true here is supposed to be like a 1 in some ROM or something. Memory type. I don't know what memory type would be, but we have some ROM address, ROM access, flash type, flash status. I'm guessing flash is flash memory, and a bunch of other bools. And then what else do we have? We have routines to initialize the memory, clean them up, enable SMRAM, which is what? System management mode? Redirected from SMRAM. Sometimes called Ring 2 in reference to protection rings, is an operating mode of x86 processor units in which all normal execution, including the operating system, is suspended. An alternate software system, which usually resides in the computer's firmware or a hardware assist debugger, is then executed with high privileges. Okay. System management mode. Why is it called RAM? Yeah, it gets its own address space, right? In order to achieve transparency, SMM imposes certain rules. The SMM can only be entered through SMI. The processor executes the SMM code in a separate address space, SMRAM, that has to be made inaccessible to all other operating modes of the CPU by the firmware. Okay, so I guess this is to enable that part of the address space. And this, I guess this is whether it's accessible. We can get the host memory address. Get host memory address. So getting the host memory address takes in a CPU-C, and the Bochs physical address, and an unsigned RW. Maybe read write. And it gives you a Bochs mem SMF bit 8U star. So I guess this is trying to figure out if you, I'm guessing what you put in is like, by calling it physical address based, like, this is the space on your computer. And then this is what Bochs, I guess, thinks the space is or something. You can read physical page, write physical page. Then direct memory access. We can load ROM and load RAM. And we pass it a path and a physical address, I guess, either to load from, and then some type, bit 8U type. And then some debug stuff. We've got this register state, which takes nothing and returns nothing. And I don't know what it does. And we can unregister memory handlers. Okay, so memory is not so. Wait, what was that called again? That was memory box.-h. And here's memory.cc. So here's let's see. This is pretty small. Under 400 lines of code. And I guess this is the implementations of some of those functions. So let's take a look at, I guess, read physical page. So we're going to pass in a CPU thingy and the physical address and the length and the data. Data must be an out parameter because we're void. And so we have this data pointer. And then we take the address as passed in and call A20 ADDR on it. I don't know what that does. It does something. And it gives you a new physical address, it looks like. That's the A20 address. And we have this memory handler struct, which we set to null. Then we check if the address, I guess we shift the address by 12 and check that it's not equal to the address plus length minus 1 shifted by 12. Shifted by 12, why? I'm not sure. But if they are, if they're not equal, then we have this panic. Read physical page, cross page address access at address OX, and then format physical address is, I guess, some macro. So if this condition happens, we are trying to read across a page somehow. And then if we're not trying to cross a page, then we have this isBIOS thing that's going to check, I guess, whether the address is in the BIOS space. We've got this BIOS ROM address, which comes from somewhere, and we're checking that it's not, that this A20 thing isn't in here. And this seems to be more BIOS checking. And if the CPU is not null, if the CPU is null, what happens? I'm not sure. I don't know. But if the CPU is not null, then we may be doing some debugging stuff, which we'll ignore for now. And then we look at to see if the address is above whatever this number is. We've got an A right in the center here. And then between this A and C, and bxmem this smram available, then I guess we're in smram memory space. And if we've enabled smram, or sorry about that. So if we've enabled SMRAM, or I guess the CPU is an SMM mode and not SMRAM restricted, then we go read the memory. And then if we're not in this SMRAM area, then we get like a reference to the memory handler by looking up in this memory handler's array the A20 address shifted by 20. Maybe that's what the 20 is for. And then while we have memory handlers, we're going to look at the begin memory, the begin part of the memory handler, and if basically begin and end. So like I guess the memory handler like operate on some interval of the memory, and we're just checking that the address is in that memory, and if it is, we'll call a read handler because we're reading, right? Read physical page. So we're going to call the read handler and then return. And then we're going to like walk down the chain of memory handlers, essentially doing a linear search. And then if we have ever gone to memread, which we do here in this SMM thing, then we do some more bounds checking. And then we call bx memory stub c read physical page. How is that different? I don't know. Oh, this is a recursive call, I think. bx memory. No. I guess memory C is like the parent class or something. And so on. Because we've got this stub. I think stub was essentially the parent class. And then if we are a little endian, then we'll set data pointer to be the data we got cast as a bit 8U star. And if we're big endian, then we're going to set data pointer to, we're casting as a bit 8U star, but we're taking data and adding to it the length -1, which I guess is going to put us at the beginning of the, if we had 1, 2, 3, 4, I guess, and we were pointing here, it would point at 4, it would point us at 1. And then address must be in range. So we do some more range checking and so on and so forth. That'll be enough for me for this function. Okay. So that's some memory stuff. We've seen a couple of things in there. One is that there's lots of bounds checking, making sure we have the ability to read that memory, making sure that the memory isn't something that it shouldn't be, like the BIOS or whatever. And then fiddling around with little and big endian and so on. AVX, CPU / AVX. I don't really know what AVX is. Let's look up AVX CPU. Advanced vector extensions. So this is a SIMD thing. I don't think I'm ready for advanced SIMD. I don't even know if I'm ready for regular SIMD. Let's start. How about CPU.h? Warning. Only Bochs CPU-C member functions can use these shortcuts safely. Functions that use these shortcuts outside of Bochs CPU-C might work, etc. All right. If I pause for a while, it's because I have to cough. Okay. Let's see. So here's CPU.h. We're reporting set jump, and not really a whole lot else. Instrumentation, decoder, and the first thing we get are a bunch of defines: AL, CL, BL, AH, etc. These are access to 8-bit general registers. And we've got this BX CPU this pointer and a general register 0, 1, 2, 3 .word.byte.r1. So these are all different because of the index, and these are all different because of the, these are all different from these because we have our H as opposed to L. L and H, I don't know. Let's look this up. Register AL, AH. Assembly registers, online tutorial. So lower and higher, I guess. So here are the 16-bit registers. Here are the 32 bits. The 32 bits, I guess we get by appending an E to the name. And lower, I guess these are the lower 8 bits and the higher 8 bits. Is that what I'm supposed to understand? So accumulator, base, counter, and data. AX is the primary accumulator. It is used in input, output, and most arithmetic instructions. For example, in multiplication operation, the operand is stored in either EAX or AL register according to the size of the operand. BX is known as the base register, as it could be used in indexed addressing. CX is known as the count register, as the ECX, CX registers store the loop count in iterative operations. DX is known as the data register. It is also used in input-output operations. It is also used with AX register along with DX for multiply and divide operation involving large values. Okay, so that's helpful. So what? Accumulate, count, data, and bogus, base. Okay, and then lower and higher. So we got that, and then these are the 16-bit registers, which now instead of lower and higher, we have X here. And then somehow we've jumped the shark and now we have S and a P. I don't know what those are. Pointer registers. Are these pointer registers? IP, the 16-bit IP register stores the offset address of the next instruction to be executed. Okay. That's simple enough. The stack pointer is another 16-bit address that provides the offset value within the program stack. And the base pointer mainly helps in referencing the parameter variables passed to a subroutine. The address in SS registers combined with the offset in BP to get the location of the parameter. Okay. Yeah, thank you. I appreciate it. AE. All right, so those are the 16-bit registers. So this must be stack pointer. Oh, sorry, we're in 30. I skipped down to 32 somehow. So here's stack pointer. Somewhere where there's a base something or other. IP, I don't know. At any rate, these are more registers. And then we have this 64-bit registers like racks, RSP, RBP. I'm not really sure what all of those do. I'm not an assembly person, as I'm sure many of you can tell. And then we've got a bunch of functions that are defines, and these are just doing things like reading the registers. And let's see. So like BX read 8-bit register regx. I think this notation means it takes values index and extended. And then we're going to AND the index with 4, which is what, like, is 10 in binary. So I guess we're getting the second set bit and checking whether that's 0, and then ORing that with extended. And depending on the result, we are going to either call this genreg function at the index, I guess at the index named index on the lower side, or we're going to call index -4 and get the higher side. So this is somehow, I think, checking whether, we need to read the lower bit or the lower part of the register or the higher part of the register by looking at its at what's set here. So what else do we have? So CPU mainly so far for the first 200 lines is about reading registers. That's good. We've got this thing, some enum, TLB control. It has things like task switching and context switching. TLB, I also forget. Look-aside buffer, translation, look-aside buffer. Yeah, okay. Is a memory cache that stores the recent translations of virtual memory to physical memory. It is used to reduce the time taken to access user memory location. It can be called an address translation cache. It is part of the chip's memory management unit, MMU. It may reside between the CPU and the CPU cache, etc., etc. So it's sometimes implemented as content addressable memory. It has a fixed number of slots containing page table entries and segment table entries. Page table entries map virtual addresses to physical addresses, and intermediate table entries, while segment table entries map virtual addresses to segment addresses, intermediate table addresses, and page table addresses. Okay, so this is essentially a table for mapping. So the TLB is essentially a table for mapping memory from one space to another. Why TLB control? So TLB control has things like task switch and context switch. And I'm guessing that what's going on is that when you switch tasks, that may invalidate the TLB. And I don't know what this other stuff is. Inv might be invalidate, inv L page, maybe invalidate some sort of page, invalidate some sort of pointer. I don't know. Move CR, CR0. I don't know. So let's look at maybe TLB, or maybe we'll just search in Wikipedia for task switch. Blah, blah, blah. Can be used to prevent frequently used pages from being automatically invalidated in the TLBs on a task switch or load of the register CR3. Normally entries, okay, here we go. Virtualization and x86 TLB. With the advent of virtualization for server consolidation, a lot of effort has gone into making the x86 architecture easier to virtualize and ensure better performance of virtual machines on x86 hardware. Normally, entries in the x86 TLBs are not associated with a particular address space. They implicitly refer to the current address space. So it sounds like current address space is essentially like a global variable that is implicit traditionally. Hence, every time there's a change in address space, such as a context switch, which we were seeing in this enum, the entire TLB has to be flushed. Okay, so that is why the context switch is in there. Maintaining a tag that associates each TLB entry with an address space in software and comparing this tag during TLB lookup and TLB flush is very expensive, especially since the x86 TLB is designed to operate with very low latency and completely in hardware. And so since 2008, they've introduced tags and dedicated hardware that checks the tag during lookup. Okay, great. But I don't think that Bochs necessarily knows about that, especially since it seems to predate that change. And so we have these things, and we need to know. There's something about reading from CR3 or whatever. Reading from one of these, I guess, changes the address space. And these are other things that might change the address space and basically invalidate cache, it looks like. And what else do we have? We have instruction branch, possible types passed to bx inst far branch and bx inst unc near branch. UCN maybe. I was going to say unconditional, but it doesn't seem right. At any rate, this is something about jumping. So I'm guessing we try to. I guess we probably try to keep things close together if it's a common branch. And then we try to reduce far branching, but I don't really know much about it. So this we can say whether it's a jump or an indirect jump, a call or an indirect call, I'm guessing call is like a function call, and the jump might be maybe more general, like you can jump within a single function. Is return. I don't know what iReturn is. Int, maybe interrupt. Then we have syscall, sysreturn, sysenter, sysexit, and UIret. Maybe that's for the Bochs UI. I don't know what UI is supposed to be. And so this is something about branching. Possible types, pass to BX prefetch hint. So this is some stuff about prefetching. I don't know what it means, but we have T0, T1, and T2. Maybe that's like type 1, type 2. And then we have access reason, pass to the internal debugger. Okay, so this is, I guess, like maybe memory access. Like, why was this memory accessed? And this is for debugging. And then a bunch of exceptions. Divide error, fault, which is maybe like divide by 0. Debugging, breakpoint, overflow, trap, bound, fault. So this is just some enum. And then we have a CP exception, error code. Near ret, is that an exception? Far ret, iret, end branch. I don't know what all that is. And then more, I mean, I know what these words are because we just saw them. I don't know why they're exceptions. I don't know. We may see, we may not. And then we have some more exception class stuff. Something that might be a trap or a fault or abort. I feel like trap is for like interrupts, right? I don't, fault. Let's look up x86 trap. What is the difference between trap and interrupt? A trap is an exception in a user process. It is caused by division by 0 or invalid memory access. It is also the usual way to invoke a kernel routine, a system call, because those run with a higher priority than user code. An interrupt is something generated by the hardware. I don't know if that's true, but maybe it's true. Traps, interrupts, and drivers. Interrupts, faults, and traps. So fault is an instruction execution faults for some reason. When a fault occurs after the fault is handled, the instruction should be re-executed again so the fault can be alleviated. Examples of faults are exceptions such as divide by 0 or page fault. Okay. A trap occurs as the result of a user space CPL equals 3 program. What is CPL? Transition to CPL to the highest level. Is this just like ring? CPL. Protection ring. Okay. Something protection level. Current privilege level. Okay. So a trap occurs as a result of user space, current privilege level 3. I guess maybe 0 is root. And then 2 was the SM RAM stuff. I don't know if that's the same. These are all the same numbering system. CPL3 program execution actions, see the table above, that result in a trap to the highest privilege level. So you're essentially saying, I need a grown-up. It's like when a kid says they need a grown-up to help me, and then a higher privilege level comes in. A trap is an event fault that is reported immediately after the trapping instruction. The execution resumes at the instruction following the trapping instruction after the trap is handled. And then we have the following are examples of process actions that can generate traps. So we have user space traps such as int3 breakpoint for debugging, int x80 in Linux, which can be inserted into user space code to force a trap to the CPL equals 0 mode. When int x80, where x80 is the vector, is executed, the CPU will transition to the CPL equals 0 and execute the handler registered for vector 80. I don't know what that is, but I guess that's a thing. And then we have privileged execution at CPL equals 3 that generates a GP. I don't know if GP is, I don't know, whatever GP is. Okay, so that's different kinds of things you can do to notify that something is amiss or needs to change or that you need help or whatever. We have some canonical stuff. I don't know what that is. We've got this function that checks whether something's a valid physical address, etc. and just more stuff along these lines. I think I'm gonna move on to another file. We've got this big endian thing. If to have big endian, we have one struct. Then where's the little endian version? I don't know. But we do see some stuff here where it's like, you know, if we're big endian, we need to do one thing. If we're little endian, we need to do another thing. All right, here's cpu.cc. I don't know if we need to look much at this. I think we, this CPU run trace thing. I think I'm going to move on and see what else we can learn about the world of x86. CPU ID. I don't know if this is for like multiple, if you have multiple CPUs, then you have like a stable ID or something. You can init. We've got this constructor, I guess. That's not so interesting. You can get the name. You can get CPU extensions, which are just stored somewhere in some array. Is CPU extension supported? I forget what CPU extensions are, but let's look at what some common ones are. An extension instruction set has been introduced to Intel, blah, blah, blah. So I guess it's in extended instructions, maybe like SIMD and stuff. All right, I'll assume it's stuff like SIMD. If CPU level is bigger than or equal to 5, then we have this RDSMR stuff, RDM-SR stuff. What is that? I don't know. -1, -1. So this is whether we support SVM, support VMX. We can enable a CPU extension, which we just like set some bit mask, it looks like. And we're emulating, so there's not really, you know, you don't need a different physical CPU. You just need to know that you're supposed to emulate other stuff. Topology leaf. Get standard CPU ID extended topology leaf. And you pass in some sub function in a leaf function. I don't know what that's about. Here's some VMX features. Virtual NMI, TDR shadow, VMX preemption filter. What on earth? Oops. VMX. Not the military thing. Virtual machine extensions is the use of hardware-assisted virtualization capabilities. Okay, so Intel Virtualization VTX, previously codenamed Vanderpool, VT-X represents Intel's technology for virtualization on the x86 platform. Okay, and then I think the other one was for AMD, right? SVM is for AMD. Okay, so this is just some, I guess, support for Intel's virtualization stuff somehow. Here's some CPU ID defines. And they have things like whether the FPU is on chip, I guess. The VME enhancements, debug extensions, page size extensions, and so on and so forth. And how is this different? CPU ID defines features, whatever EDX, then ECX. Just like more settings. I don't know how EDX and ECX differ, but these are different things I guess your CPU can support. And we'll just like kind of quickly glance at them and see if anything looks especially fascinating. I don't know enough really about this world to know what here is interesting to look at, but really it's just a bunch of defines that are some bytes. Essentially they're enums. Here's data transfer 8. Whatever data transfer 8 means. And what do we have? We're in a CC file. I don't think we had a header file for data transfer, did we? No. Okay. But let's look. So, whatever attribute reg parm n move eb gb m move eb ibr, and we've got this write 8-bit register. Whatever I is, I guess we passed in I is some instruction. We're getting the destination. We're passing the destination. We're looking at extend 8-bit L, I guess L for lower, and then whatever IB is, some register stuff. So I guess this is data transfer as in like moving stuff around registers. And then we call BX next instruction after each of these. ATR reg. So reg is presumably register. Parm, I don't know what parm is. And then I don't know what ATTR is. Here, 16 should be basically the same, except now we have to call CPU resolve address on I, and then we write the virtual word. So we have some instruction. We get seg, which I guess is some segment, and we pass an EA address, which we got from the resolve address, and then IW, I guess, is I word, instruction word maybe, and then here we had IB, right? Maybe IB is like instruction byte. I don't know. Can we find BX instruction? Class BX instruction. Yeah, they don't tell us what it is, but this seems to be the... this is some model for an instruction, and it's got some opcode and some length and some execute pointer, and you can tell what the next thing is. And I don't really know enough about all of this stuff to know what is what, but this is like their model of instruction, and we have things like I'm guessing IW must be word, mod rm form, mod, I don't know. IW I'm gonna guess is maybe word, IB maybe byte, and then maybe these are two wide words. I don't know. So I really have no idea what this data transfer is. Control transfer I'm gonna guess is basically register transfer, except we're not using data registers, we're using control registers. And we get stuff like call far. So I guess this is like maybe function calling. Oops, where did call far go? Call far 16. So we're gonna call bx far branch origin, and then invalidate prefetch. So whatever we prefetched based on what I assume predicted the branching was going to be, seems like we invalidate it because we're going to do this far call. And then we call RSP speculative. And then check if we're in protected mode, et cetera, et cetera. And then we push 16, BX CPU, this pointer, sregs, some value, and then we push 16 IP. IP is what? The instruction pointer, I guess. And then we load some stuff, etc. Hello, QSM. So now I want to see what RSP speculative is. Then maybe we'll see what RSP commit is. It seems like we're getting into speculative execution. I'm going to delete a bunch of these. Do we care about F? I don't know. I think I'm just going to delete everything except we're going to look at speculative execution. In fact, give me about 2 minutes and I'll be right back. In CPU.h, we have this defined for CPU. What is it called? Speculative something? Speculative RSP. Let's try this again. RSP speculative. I should be unmuted now, right? Thanks, QSM. All right. So we've got this Bochs CPU, this pointer, speculative RSP is equal to true. So we set just this variable speculative RSP to true. And then we have these two, we have preserve RSP and preserve SSP. And preserve RSP sets this preserve RSP variable to RSP, and preserve SSP sets this preserve, I guess, SSP variable to SSP. RSP and SSP, I don't know what these are. I guess they're registers. Are they registered? Let's ask the AIs. Tell me RSP and SSP as it relates to Intel 386. Two important registers. So RSP is the register that holds the address of the current location in the stack. Okay. So that's where we are in the stack. SSP is the stack segment pointer. It's actually a legacy term and is synonymous with SS, the stack segment. In protected mode, which is the mode typically used in modern operating systems, the segment registers like SS are used to access different segments of memory. SS holds the segment selector for the stack segment. So this, I guess, tells the stack like which part of memory it's accessing. And so these together, yeah, here we go. Together they facilitate efficient stack operations. So these together, I guess, tell you like where you are in some sense. And so that's why we're preserving them when we do speculative stuff. And what else? I guess we need to find out what happens when this variable is set to be true. So we see some stuff in SVM. And we see some stuff in exception and in VMX and in tasking. In tasking, we're just setting speculative RSP to false. And here in CPU.cc, we just set it to false. So it seems like we're only really reading it in SVM and exception. I'm going to guess exception is not the most important. And what was the other one? VSX maybe? VMX. And SVM and VMX are the AMD and Intel extensions for virtualization, I think, right? Didn't we just confirm that? Okay. Oh, so here we're setting it. Is that what we were doing? Oh yeah, we're just setting it to false. But here it's being read. Let's see if we use this anywhere else. Oh, here we go. Yeah, so if speculative RSP is true, then we set RSP to be the previous RSP. VM exits are fault-like. Restore RSP, etc. Okay, so this is just the restoration logic. Is that what we're doing in VMX too? Wait, what? So in SVM, I think we just copy pasted the code from VMX based on the comment. Huh. So where do we where else do we read this? Not that. Go away, whatever that is. Let's ask how does Bochs handle speculative? I think that's what this is for, right? Must include Bochs. Do we really have no hits? Okay, whatever. We are currently adapting the x86 dynamic translator QEMU3 to be a Verx. Other possible Verxes can include the stem system, which is based on Bochs, Bochs itself, or Valgrind. This is from some paper on speculative execution as an operating system service. Yeah, I don't know. Let's see. Bochs, being a full system x86 emulator, doesn't directly handle speculative execution in the same way that modern hardware processors do. It's a feature found in modern CPUs, blah, 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 blah. However, Bochs does provide a simulation of the x86 architecture, including features such as pipelining, instruction decoding, and out-of-order execution. Here's how they might simulate. Well, I don't want to hear about might. I feel like there must be some way of... So here's FPU. I'm guessing that's floating point unit. How about prediction? Predict. Indirect branch prediction barrier. Single thread indirect branch predictor supported. That's one of the CPU ID things. Tiger Lake. So we do have some like CPU database that has some, I'm going to guess is just like it records which features are enabled on which chipsets. So if is CPU extension supported, BX, ISA, blah, blah, mitigations, then we're going to set leaf EDX to a bunch of stuff that we're orging together. These are like, I guess, setting flags. That these are the things they support. And so this is some sort of like configuration information for the Tiger Lake CPU. And they have a bunch of other CPUs. These are all the Intel ones. Maybe they have AMD. Yeah, they have Intel and AMD, including Ryzen. Okay. But, so here's another reference to the speculative stuff. And again, we're just like restoring. We'll close this out. What if we just look in issues for something? What if we just look in issues for Spectre? No? How about Meltdown? How about Branch? So we do have this branch near, branch far. Let's try asking Gemini just to tell me how does i386 speculative execution work? Released in some, is that a camel? No. 1985, I guess is what it's trying to say. Okay, so it says it predates, I don't know. So I don't know what this RSP speculative means. What if we just search for Bochs RSP speculative? So it's maybe we'll just take a look at just where this is used. It seems to be like setting aside, you like flag some like critical looking sections with it is how it's used. You call it once here at the beginning, and then I guess you call it down below usually, right? So at 221 and 308, I don't know if this is the same function. Doesn't seem to be. I guess you said it, and then we have RSP commit. So I guess what's going on is that when you enter a speculative section, it's something that you might have done in error, I guess. And maybe when you call commit, that's when you're committing to the stuff you computed. And then what takes you out of it? Maybe just error, BX error. So let's see if that is a reasonable guess. So RSP speculative will set this thing to true. So I guess I thought you were like adding it at the beginning and oh no, you add RSP commit at the end. When you call RSP commit, you set speculative to false. That's all you do. And whatever you computed for the RSP and SSP speculatively is now law. And then I guess we saw in some of the error handling code that we checked if speculative RSP was true, and then if it was, they rolled back in an error. So I guess that's what's going on. So we have this BX error thing, Bochs error. Log this error. I guess after Bochs error, so maybe Bochs error is just logging, and then where did we see? We saw, so here's the error handling code. When does this get called? VM exit. VM exits are fault-like. Let's look what when VM exit is supposed to be called. Hardware virtualization is based on the philosophy of trying to trap all exceptions in privileged instructions by forcing a transition from the guest OS to the VMM, called a VM exit. You can call this an improved version of the blah, 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 IBM S370 virtualization methods. So we're going to try to trap all exceptions in privileged instructions. So if it happens in the VM, then if it happens in the guest VM, then when we see an exception, we're going to, I guess, like notify the host VM. Is that the idea? Or at least the virtual machine manager? No, I'm sorry, not host VM, but host machine. I think that's what it's trying to say. And so VM exit is like we're leaving the simulated world, I think. And yeah. And so here's RSP commit. So if we have something like this, then why is this speculative? What can go wrong? There's one little weirdism here. It is possible to use SP in mod or M addressing. Maybe write virtual word can throw an error. I don't know. How about I think I saw maybe it was called exception or error. GitHub. Okay. Let's look here again. And then look for, what was it, BZ error? Or no, BX error. Why is this not doing what I want it to? How about we look for BX error first? Maybe in stack.cc and see if there's RSP stuff in here. No. Whatever. Fine. I guess I won't find it. Oh, here we go. I should just open this one. Flag control. So exception, what happens when you call exception? Exception.cc. If exception generates an error, push this error code. So we set some exception stuff, set push error to false. We check if vector is less than handled exceptions. What is vector? Vector is a, I don't know what IDT is, but it's 0 to 255. I don't know what that means. I guess it sounds like vector is really an int. That's less than 255. But maybe it's a vector of ints or something. So at any rate, if vector is less than the handled exceptions, we're going to push the error onto some vector, I guess, list, and then get its exception class and type. If it's an unhandled exception, we're going to panic with bad vector. And if we're down here, then we probably haven't panicked. I'm going to guess panic is pretty disruptive. Excluding page faults and double faults. Error code may not have the least significant bit set correctly. This correction is applied first to make the change transparent to any instrumentation. So I guess we're doing something about setting the least significant bit. And then we may debug some stuff. I guess like this is probably some sort of breakpoint saying that we've met an exception. If we're in real mode, then we'll set push error to false, not int, no error code pushed, and set error code to 0. And then we call instruction exception with the CPU ID, the vector, and the error code. We might do some more debugging. If we're in VM X, then we're going to do this VM exit thing, which will, as we saw, this is the thing that causes RSP to be reset. So this is what I was looking for when we're doing speculative. Similarly for SVM, we're going to do this thing that I guess exits the VM and notifies the VM manager, and then we have some more exception stuff. All right, so that's all very interesting. I don't think I can really go on to another repo today, but hopefully, I'm hoping later this week I'll be able to do a longer one. I think I'm going to leave this here. This was an interesting repo. There's a lot more we could get out of it. I wanted to keep this to about an hour, as is my usual thing these days. I'm trying to think. Well, we didn't really see any of the SIMD or vectorized instruction stuff. That all I think would largely be lost on me, not having much of a background or an understanding in the hardware size of things. But we did see some cool stuff, and it's at least given me like more of a sense of like maybe like an anchor point for how some of this works under the hood. And the code itself seems to be like very clean. There was no point at which I really felt like I was lost, or I never felt like, that the I guess one way to put it is that in places where I was confused, it seemed really clear that my confusion was about a lack of domain knowledge rather than a lack of coherence in the code. So all of that's really nice. This seems like a nice project to take a closer look at and learn more from if you're interested in this, in the world of virtualization, or understanding how things like assembly and hardware work. And I guess I will leave it there for now. Thanks for watching.